Mr. Chairman, ladies and gentlemen, I'm honored and proud to have the opportunity to speak at this conference. Today I would like to present my paper, A Network Traffic Collection System for Space Information Networks Emulation Platform. My report will cover the following aspects, and in the first part of the report, I'm going to begin with the background and purpose of our work. The Space Information Networks System is a network system which takes the space platform as a carrier to acquire, transmit, and process spatial information. The Nanjing University team has constructed a laboratory-scale network emulation platform which applies visualization technologies to emulate space information networks. As shown in the figure, the space networks emulation platform is divided into 4 planes, including the logic plane, the control plane, the data plane, and the analysis plane. In order to evaluate the performance of space network scenarios, it's necessary to conduct in-depth analysis of traffic data in the emulation network environment. Network traffic collection system is an important part of the emulation platform. This paper uses visualization container technology to share network namespace, and uses T-Shark to capture and process network traffic, using big data technology and Elasticsearch database to realize data storage function. A method of parallel collection is proposed. At the same time, reasonable allocation of system resources, distributed deployment, load balances through file sharing, network traffic collection performance of the emulation platform is further studied. The network traffic collection system is integrated in the data plane of the space networks emulation platform. Next, I will introduce architecture of network traffic collection system. First of all, container technology and big data technology are used. Based on the ELK, the collection system can capture, process, and store network traffic data. Secondly, in order to further improve the collection performance, the system parameters are optimized and a parallel processing method is proposed. The architecture of our designed system is illustrated in the figure, which can be divided into network traffic capturing module, processing module, filtering module, storage module, and visualization module. The capturing module is to ensure that the network traffic data is completely captured without loss of packets. All captured packets have a lot of information. Network traffic processing module implements the processing function. The filtering module is mainly responsible for filtering information according to rules. The storage module stores useful information for subsequent analysis. Data visualization helps effectively understand and analyze massive amounts of data. The above modules work together to finally store traffic data in the database in JSON format. Data can be written and displayed in real time. Next, I'm going to introduce the best settings of Firebit and Elasticsearch in the system. Elasticsearch database is a distributed database, so the indexing of Elasticsearch is usually broken into different parts. The data distributed on different nodes is called shards. The number of primary shards affects write performance. There are 2 ways to reference when writing data. Synchronization means that memory data is brought into disk at fixed intervals. The figure shows the impact of different primary shards and different synchronization mode on performance. Performance improves as the number of primary shards increases, compared with synchronized writing. A synchronized writing has a great improvement in write performance. The right table shows the performance impact of different replica shards. We can temporarily set the replicate shares to zero when a large amount of data is written, and then restore it later. This not only improves the writing performance, but also ensures the security of the system. The results show that when the number of primary shares is 8 and the number of replicate shares is 0, the write rate reaches a reasonable value. Under the limited hardware resources, with the increase of the number of emulation nodes and network traffic data, the performance of serial data collection has been unable to meet our requirements. The parallel data collection method is adopted to improve the collection performance. At the same time, distributed deployment is carried out in order to make reasonable use of system resources. As shown in the figure, all network traffic captured by one T-shack is serially stored in one log file and monitored by one 4-bit file. This method does not make full use of resources of the server, and when the traffic scale is small, the rate of serial collection method can meet the demand. So, we collect traffic in segments based on a fixed time period. Every once in a while, we turn on a T-shack capture and press the traffic in the current time period, and turn on a 4-bit to monitor and filter log files to achieve a parallel effect. It saves the pressed data in JSON format. In this way, in subsequent analysis, the queried data can be used directly without additional processing, which saves processing time. At the same time, as shown in the figure, T-shacks and 4-bits are deployed in a distributed way. T-shack is deployed on a server. It shares the log files on another server via NFS files. Files are monitored and filtered by 4-bits. This kind of distributed deployment makes reasonable use of server resources and reduces the contention of CPU and other resources between traffic collection system and emulation system. Now, by using the above method, we can get the result. The amount of parallel processing is one metric. The number of different T-shacks has an impact of writing performance. The table shows that with the increase of the number of T-shacks, the write rate of a single thread will be reduced, but the overall write rate will increase greatly due to the increase of the total number. It can be observed that the limited by hardware resources, performance cannot be infinitely linear improved. When the number of T-shacks is 20, the system resource bottleneck is probably reached. The figure shows the time comparison required for single serial and multi-channel parallel processing when processing the same traffic data. The results show that the parallel mode has improved performance and nearly doubles. In this paper, we introduce a network traffic collection system based on container technology and elastic search database. Based on the space networks emulation platforms, we evaluate the performance of the system to collect massive high-speed network traffic. The system can collect Gbps network traffic per second. Moreover, the system parameters are optimized and a parallel processing method is processed. The experimental results show that the system can collect massive high-speed network traffic in the space networks emulation platform in real time under the condition of limited hardware resources. Thanks.